Eventually, this will actually be lower.
All right. Let's get the process started. So reminders for upcoming things. It's Tuesday. On Tuesdays, we always have the same thing. What is this? Peer reviews. Today's peer review day. So I revealed that something like less than an hour ago. Please make sure you fill that out by tonight, if at all possible. If you need to submit it late for some reason, please let me know, and I can deal with that on a case-by-case basis. But I don't like to reveal it too early, because if I do that, then people fill it out without a week's worth of experience to do the grading. Sometimes to do it the same day that I need it to be due. I don't like doing that, but I feel like this is probably not a crazy amount of work, or at least we should be putting in more than 20-30 minutes into writing all this out. It's kind of a cap of what I think is reasonable for all of this. So let me know if you have concerns about it. Tomorrow we have our lab, we have our client meeting. Tony is getting ever so excited, but ever so anxious to see what everyone has been up to over the last few weeks. I talked to him about it this morning, and he just looks giddy. I can't wait to try to break these. We'll see what happens. Yeah.
Sorry to bother. Question. So for tomorrow, do you also want us to create some PowerPoint presentations to guide through, or?
There should be, yeah, there should be nothing aside from the code and however it is that you introduce that back. So introducing yourself, talking about what you've been up to, leading up to either putting one of your machines in front of him, or if you think that it's going to take not too long to do this on his own machine, then go from there. But be a little bit flexible. You don't know whether he's gonna walk into the room with the machine. So you may need to have kind of some things figured out with regards to how is this demo going to go based on what the client wants. You don't really know that in advance. All you can have is a good project and an adaptable personality. Question?
About the peer review,
Yeah.
he asked about what was their contribution to the project of the other developer in the team. Should we grab that information from scratch, or should we ask the person what did you do the past week?
I would say grab it either from Scrum or their GitHub commits. So you can say all GitHub activity is publicly accessible. If they're not communicating, then you don't know what they're doing, and that is a problem that needs to be addressed in and of itself. You should know what everybody else is working on, because it should be apparent. It should be part of the project to know what everybody else is working on a daily basis.
So if it's not documented, it didn't happen.
Yeah, that's kind of how I would be treating it. And if you realize that there's no documentation, maybe you would want to reach out and say, hey, I actually don't know what you've been up to. Could you work on documenting that more thoroughly so that in future weeks I have an easier time with that? For this week, let me know what you've been up to so that I can better address it. But yeah, to the best of your knowledge, what is this person doing? Everyone should have a very public appearance in their group. Great questions. Over the next couple of days, I'll be collecting all of that information, and again, I may be reaching out to some people where I start to feel like there may be some concerns about how the group is working with you, your position in the group, if you're vastly overrating or underrating your own personal performance in the group. All of those, I feel like there's something you can learn from. So I may be reaching out to you. That does not necessarily mean that something bad is happening, but it may mean that we should open a dialogue about something. We'll figure out what that is on a case-by-case basis. Any other questions before we get started? I guess there's one more thing that I want to talk about. The final code is due Sunday night. So Sunday, 11:59 p.m. Sometime before then, please merge to main. And that will be your final code submission for the sprint that will be graded. So there is time between Wednesday and Sunday. Remember that. I'm not grading you on anything else on the rubric aside from the professionalism and kind of the design of your solution from Tony's perspective tomorrow. So you do not need to have absolutely everything finalized. You will have between tomorrow and Sunday night to fix anything outstanding, implement anything that didn't get done, continue to show that agile process. Anything else? Today's class and the next couple of classes that we have in here, so not tomorrow, but the next couple of classes we have in here today and Thursday are gonna be about testing. And I'm assuming that people have seen some kind of unit testing content and have some experience writing some unit tests. That's kind of the assumption that I've been under. Would you be able to and willing to kind of raise your hand if you feel like you are lacking in your own preparation for testing, writing unit tests? There's nothing wrong with that whatsoever. This is kind of to gauge where I feel like the class is, to get a sense of the angle that I should attack this from. So, yeah, some people, good, it's good.
I blame on the fact that I had a Mac.
Yeah,
That happens. We all have different experiences through this curriculum. So even people who are raising their hands, I don't attribute that to you. I attribute that to a number of factors that got you to where you are today.
And the fact that Timber was writing the project, so we had to use.
Yeah. So we're gonna start by talking about kind of testing in the abstract or broad, just like what testing is, why do we need to do it, what are the different kinds of testing, when should those different kinds of tests be written? And then we will dive into a little bit more of the specifics on each of the kinds of testing. Depending on how people feel, I have some content prepared for at different levels of that kind. So maybe I start talking to some people as well and figure out what's useful to augment what you already know. I love this quote at the start of this: "Error is the human, but to really foul things up, you need a computer." That kind of makes sense, right? Your mistakes around you affect something that is very local to you. Even if something really bad happens, you get in a really bad car accident. You know, maybe you mess up your immediate family, the people you collided with, their immediate family, but it's kind of localized to what you have reach over. As soon as you start writing software and that software starts breaking, you can actually start affecting significant numbers of people in really bad ways. So to really foul things up, to get that level of outreach, you either need to be a politician or you need a computer. All right, so software defines behavior. This makes sense, right? Whatever it is, however it is that you interact with technology, there is software behind it that makes that technology work. So it doesn't matter what that is, it's very wide reaching. So software today is bigger, more competitive, has more users. Everyone is using so many different kinds of software that in general, outreach is large. Lots of people using lots of technology for lots of reasons. There's software in embedded systems that is actually part of the hardware. So anything built into an airplane, a spaceship, a watch, a phone, a lot of that is actually embedded in these systems. So writing tests for these are very crucial because you can't go back to a lot of the embedded systems. You know, you launch a spaceship into space, you find a bug in the software. You can't fix that bug once the spaceship is light years, hopefully eventually light years away, but eventually it's moving farther and farther away. And there's no, you can send some predetermined signals back, but you have no ability to interface with that software. So it's especially important for embedded control applications, but in general, it's good to have good testing practices. Anyway. Agile is kind of it's a process where everyone is capable of stepping into multiple different roles. And the role that you take on is based on the project's needs that you are in. So in Agile, you may be a primary developer, but you will also need to write tests for the code that you produce. Tests are the main way that you prove that you developed what you said you were going to develop. You pass a bunch of tests, you go to the tests to say, if I hadn't implemented this correctly, these tests would not pass. So that's what we mean when we say here the key to functional requirements. When the client says, I want you to do something for this, you can just say, I've done it, but to really be believable, you have to have the tests to back it up, that say these tests that were written pass. And because of this, I have developed what you want to be developed. Tons of costly software failures, I'm not gonna go over these, a lot of them are outdated at this point. But I think I introduced them pretty well in the intro lecture for the course. The big point is that the loss due to poor software in the world is staggering. So we need our software to be dependable, and we really don't have dependable software without testing. We can go through code reviews, we can do everything else in the world, but really testing is the way to show it to others outside of that immediate code review that our software works, unless you're willing to go through formal verification, which, as we talked at the beginning, is a very tedious process. So all sorts of documented failures. More documented failures. As we move forward in time, safety has become more and more important. Security has become more and more important. We have more real-time software. It's not something that you publish and then it goes out into the world and then it comes back to you. It used to be that you'd release an application, people would use the application, and you would have a year-long cycle between releases to fix the issues. And people would just use the buggy software for a while until it was fixed. But now we have real-time applications everywhere that everyone is interfacing with, which has required us to develop that agile mindset where there are daily builds, weekly builds. Embedded software is everywhere. And testing on embedded systems is very important. Bigger programs, more users, security. I think we've said it kind of all at this point, but. And then, of course, everything interfaces with the internet, and the internet has wide reach. So how do we plan for this? When you're sitting down to start a large project, what is it like to actually interface with how do I create something that by the time I'm done has this abstract quality to it, that it is quality software? You can't really test that in. You have to plan for it from the beginning. From the very beginning, you're going to be, throughout the entire development process, you're going to be thinking about how do I produce something that is as good as I can. We can break this quality down into two main components: verification and validation. We'll start with validation. You can link this to the concept of prevention. Are we building the right product? And this just means that at the end, did we make a big mistake and are we shipping the client something different than what they asked for? So you're preventing some future issue by making sure that you're doing the right thing. Verification is once you have something, is it constructed correctly? Does it do everything that we need it to do from kind of the final product's perspective? So validation, verification, you need both in order to get that generic high-level quality tag. And then you need them to be independent from each other. So there's a concept of IV&V, independent verification and validation, is used as a kind of buzzword in industry. And this is independent from the actual development taking place. You don't want programmers who think that they implemented everything to also write the tests, because if you have programmers who aren't thinking about a particular aspect of the program, obviously they're going to be biased when they write the tests towards what they understand, what they've programmed, what they're planning to program if you're writing the tests before you write the code. So this ends up being pretty expensive, so it's not that everywhere, but if you can put different people on these problems, you get critical thinking from different perspectives. All right, we'll start with validation. What techniques do we have for validation? Are we building the right product? So we can look at a lot of what we have talked about so far for how do we ensure validation is being looked at? So code reviews, meetings to evaluate your specification document, your design documents, the plans that you make, the diagrams that you produce, going through and actually formalizing your requirements, formalizing your specifications, and having some kind of code standard. All of this is meant to help with validation. There are also, of course, code auditing standards, and this is usually even outside of the process of the code review. There may be someone who goes through and looks at all production level code to make sure that it adheres to company standards. So all of those for validation. Verification is where the typical testing that you're used to comes in. So here's where we actually write code to make sure that the product that we produce is performing what we think it's performing. So all of your unit tests, as well as all of the different kinds of tests that we will talk about throughout the next couple of days. So unit testing, integration testing, system testing, regression testing, performance or load testing, and acceptance testing. Has anyone heard of all of these before? Do you know what all of those are, or how to kind of map them at a high level? I feel like that's worth going over at a very high level. We'll eventually go into them more in detail, but I kind of want to talk about what are these terms, what do they mean? So unit testing is the smallest form of testing. It's meant to test a very small code block. Could be a single line, could be a few lines, but you generally don't want to write a unit test for more than a small method. Because you want to minimize the number of failure points in that unit test. You want to ensure that if something goes wrong, you can quickly pinpoint where in the code something happened. If there are 20 steps to the code, there are 20 possible failure points when a unit test fails. You actually have to go through and use critical thinking and maybe even write some additional unit tests to figure out why that unit test failed, which is not ideal. Integration testing is something that rears its head when you are working on larger projects, developing independent components, and when you bring all of those components together. So for instance, what you all are working on right now, you're not all working on the same part of your group project, but you have to work in parallel. So as you complete these independent pieces that work according to the best of your knowledge and put them together into one application, do they still work? Do they communicate with each other correctly? Those are the kinds of tests that you need to write after the fact, after all of these application components are implemented. You have integration tests where this piece talks to this piece, talks to that piece, returns something to this piece. Does that whole process work? Those are what integration tests are. System testing is once you have the complete, not just for this sprint, but once you have a complete system together. So this could be at the end of a sprint, it could be right before a major release. You're gonna test the entire system together and make sure that not just the components work together, but does the entire system do everything that we need it to be able to do? It doesn't do it in the way that we talked about. Mapping the actual product to the design. Regression testing is what happens when you have multiple releases of the same product. You can imagine a situation where you released version 1 of something and eventually you continue developing. Version 1 was perfect. Version 2 gets released, but some of the code that was written in version 2 breaks some of the functionality in version 1. So regression testing is ensuring that tests that used to pass, functionality that used to be there and is still part of the requirement, still works after you've added on additional features or gone through a complete code rework, done some digging and changed up how things are represented. Maybe you implemented some design patterns. And you wanna make sure that your code is still performing the same that it did, just more efficient. Or opens up some additional ways to develop further. Load testing is done with regards to usually servers. This will be once you can throw a bunch of requests at something. Let's say you're making a game, and as a few developers, you can make a few accounts, and you can be playing the game at the same time as your fellow developers. But as soon as you release it to the public, and it becomes the next big hit, and hundreds of thousands or millions of players are trying to play at the same time, do your servers support this? So you can actually simulate this, and you will want to make sure that you simulate it to know and have tools available to determine when your servers are reaching capacity, people's requests are slowing down, how does that affect things? Quality code, but as soon as a bunch of people are trying to use servers at the same time, maybe they experience slowdown. There's no way to check that in your code without actually looking at what happens with your servers. And then acceptance testing is kind of the end user's goal. When you throw this out into the real world and users start giving you feedback, this says that what we designed to be intuitive is actually intuitive. So it's a more abstract kind of testing, but it's very important to get that kind of feedback. You can do this through surveys, you can do this through data collection, but ways of ensuring that the public is interfacing with your product the way that you intended to be designed. All right, that's the high level overview of all of these different kinds of testing. We'll go through them in a lot more detail eventually. If you look at companies in general, half the development budget is on testing. Companies don't like spending money frivolously. So that tells you that this is actually worth the cost. Testing is the main activity that's done after the design. It's not development, as you might expect. It's actually testing. People spend more time testing than they do writing code. This shouldn't be a huge surprise, hopefully. Usually you need more testing code to verify that something works the way that you intended than it actually takes to write that code. If this is not how you have been handling your development in past classes, that's because it's a nice environment for you to learn something through the process of developing. You don't want to learn developing and testing at the same time. But I get a little bit of pushback when I say testing is more than half the battle. People say, well, historically, I've never done that before. But you're gonna start making more and more vital software, more and more complicated software that isn't just for a lab that has a pass-fail or a few possible grade outcomes, where it's really easy to determine what went right and what went wrong. This is gonna be hidden for a long time, so testing becomes much more important. If you don't test as much early on in your development, the overall cost of the project in general increases. If you're trying to run software on particular hardware, then even more testing is required. So let's say that to develop this next great game, we all buy ourselves fancy gaming rigs with 4090s and I don't know, whatever the most recent Intel CPU chip is. We buy ourselves the fanciest machines in existence. And we now need to figure out, is this playable on different systems with different combinations of hardware? What do we need to do to ensure that it works on all of these machines that we would like it to be able to work on? Just because it works for us locally doesn't necessarily mean that it works in different systems. So if you have hardware software integration, you'll need to make sure that you know exactly what hardware you are deploying this on.
Several issues in the past 5 years that I've had.
It's common. So it needs to be part of the development process. It needs to be something that is thought of and tested to make sure that it minimizes user issues. Because it looks really bad if you haven't thought this through. You should always be able to validate every test that you write. Make sure that you can say, this test has a purpose. If you're just writing a test to write a test. I get questions all the time, how many tests should I write for this code? And the variable is not the number of tests that you write. It is the coverage of your code. We will get into this concept of code coverage eventually. But this is something that is necessary, is actually tracked, or can be tracked on GitHub. It's for a future sprint requirement. So how much of our code do we plan to have tests written for? There's kind of a diminishing returns there. The first tests that you write are for the most important critical pieces of your code. Is it worth making sure that every line of your code performs exactly as you want it to? That's a lot of work. That's gonna take a lot of time. That's a lot of development costs for a company. When do you stop testing? There's no right or wrong answer to that, so it's really difficult from a manager's perspective to say 15 tests should be enough. It depends on the quality of those tests. It depends on what code those tests are targeting. It depends on if you can come up with a test that's kind of all encompassing. If this is going to fail, then this test will cover it with a single test. Or you need to write 6 tests to get that same level of coverage, or only get half that level of coverage. So stop thinking about testing in terms of how many tests did I write, and more in terms of did I capture everything that I think could go wrong in a major way? And start thinking in a more minor way, than that. And you end up with a testing budget. I have 10 hours to worry about testing this. Great, how are you going to utilize those 10 hours to produce the best coverage that you can? Testing itself requires planning. You don't just want to hop into this just like you don't want to hop into code. You want to make sure that you have a testing plan. So for every test, you should have some statement you should be able to validate through that test running. Try to write these in English in your planning. So what are you trying to validate or verify about your project as you actually write these tests? If you don't test, things cost more. We figured this already, but you can interface with some good test writing tools as well. And in general, if you're working for a company that is forcing you to do all of this work by yourself, coming up with all of these tests from scratch and don't have some built-in testing tools for you to use, they're reasonably cheap compared to the cost of development time, compared to the cost of humans are expensive. Our time is valuable. If there can be a one-time cost for software that vastly reduces the amount of time that it takes to produce the same level of code coverage, that's a worthwhile investment. It's something that you should advocate for within your company. Your higher-ups may not have any idea that these tools exist, or the relative cost of these tools, or how much of the time that they're paying you is spent on menial labor that can be replaced and optimized by software. So know the kind of software that's out there. As you go through your test planning, what should you be producing? What should you be able to hand off to someone to say, here's the plan that I created? You can go through a test approach. What objectives? What is the scope of each test? Entry and exit criteria for those tests. When are they going to be run? Key dates. How frequently is this test going to be run to ensure that this is happening? So kind of a big plan. Moving from the test approach, the test scenarios, high-level descriptions of the functionality. What aspects of our program need to be tested at a high level? How is that going to happen? From those, you build the test cases. This tells us an actual logical procedure to test a feature or an aspect of a feature. So you break that down into, to test this feature, we need these sub-features tested. To test each of these sub-features, we need to write tests that target this and that and the other thing. And if we do that, that should be the super majority of cases of interfacing with this feature. Conditions and expected results. What do you expect to happen when this test is run? Do we expect success? What happens if there is a failure? What does that mean? Cycle control sheet, scripts. All of these are useful. Questions on anything we've covered so far? I know this is not the most thrilling lecture. It's definitely, it's a bit dry. I'm right there with you, but it is important to kind of change your perspective on writing code from being very code writing to very testing focused. Any thoughts so far? Anything anyone wants to share? Any experience with writing tests and how that has affected your development? Any experiences not writing tests and wishing that you had written tests? I think that happens pretty frequently. You get a sense of, I have this under control. You dive into it and you realize I'm way over my head and I need some structure to this that I wish I had produced before I started writing it. So planning for tests and writing tests can be a significant part of that structure. Especially as what you need to produce gets more and more complicated. So what does application testing actually look like? While you're analyzing what the kind of designing, creating the specification document and then designing the solution from that, you'll come up with some kind of testing plan. This should be done before you start writing code. The question will boil down to, when do you actually write the tests? Do you write the tests before you write the code, or do you write the tests after you write the code? But regardless, the plan for the testing should be in place before you start writing the code. So as you're designing, plans for your unit tests, plans for your integration tests, plans for your system tests. Depending on your company, depending on your preferences, when that testing is done, like I said, it could be either before you start writing code, and that way you write the code kind of to the tests to make sure that the tests pass. And if you design good tests, then you will write good code. Or you can write the code, write the tests to make sure that the code does what you thought it would do, and then go back to the code and fix any issues that the tests reveal. If you have to do this process, if you have to plan out your tests, that's another good time that you can be communicative with your group to make sure that you're all on the same page. Any groups had an experience with not being on the same page yet? Yeah, a couple of groups. I've seen it happen. There have certainly been some issues that have developed because of some communication falters. And that's okay, you're all learning about this, but minimizing how frequently that happens is something that you'll learn over time. Testing techniques can come down to a couple of different variables. You can have static or dynamic techniques. So static testing happens without actually executing the code. Dynamic means that you are actually executing the code as these tests happen. This can also be called black box and white box testing. We'll go into that in a little bit more detail. You've heard either of those terms before. And then tests that you write are either automatic or manual. If they're automated in some sense, that means that you can attach this test to some other process. And it can be run independent of any developers once it has been written. A manual test, on the other hand, is something that actively involves a person every time it is run. Testing these days is very much automated. The goal should be that the tests that you write are able to be run independently of needing a person. That said, something like acceptance tests need people. You're writing this application for people to use, so you will need to interface and do some tests with the end users to make sure that you're developing the right product, the product that you developed is usable to their standards. We talked about the inspection, the walkthrough, and the desk check, as this calls it. So I won't go into too much more detail here. We have very thorough testing at the top, very less thorough but more time-saving techniques at the bottom. Here we have the actual types of tests. We talked about unit tests. You can break programs down into what we call modules, very small pieces of code. They're tested by themselves, not within the scope of a larger program, to try to figure out, does this one small module correctly spit out outputs given some number of inputs? So you're writing input-output pairs to validate that this code produces the right right output given the correct input. Integration testing, bringing everything together. All of these different modules that were written at different times by different people, bring them together. You'll integrate them in some way such that you have a more cohesive whole. By top down here, this means that we're going to be thinking about testing the entire system, and we're gonna break that down into kind of a depth first search. You can imagine like a tree. We're gonna take these two subcomponents and bring them together at the top level, but those aren't complete. So we're going to break those pieces down and kind of combine those and test those. So kind of depth first search look. Regression testing, verifying something that used to work, still works, given any changes that we've done. System enhancements, patches, configuration changes, anything that we've introduced to our code base. System testing, everything the system comprises of. This is where we're actually testing it on particular hardware, we're testing it with particular use cases, so users doing the same thing over and over. Performance testing, responsiveness and stability under particular workloads, making sure you have the server support, and acceptance testing, testing by end users, exactly as I said. Questions on anything so far? I feel like people could be jumping up and down during these lectures to keep blood flowing and keep the engagement high. I know this is not the ideal way to learn. I don't love lecturing like this. There's also not a great way to introduce kind of an abstract way of testing. Once we get down to how do you unit test in Java, we can do something like that. How do you integrate? How do you write integration tests? We can do a little bit more with that. But getting through the overview. Overall goal of testing, does the system satisfy the requirements? Pretty straightforward. Good tests reveal errors. Good tests don't just pass. They should fail as frequently as they can. If the test should fail, it should fail. Failing is a good thing. It allows us to correct an issue with our code. You can think of tests, breaking them down into three major categories: typical system use, critical system use, and abnormal system use. So you can write tests that this is the everyday interaction of a user with this program. Does it work? Critical system use is what happens when something major happens. Does it still work as intended? Is the structure there, is the variable there to be able to handle something that might happen on an everyday basis? And then at normal system use, what happens in those edge cases? What happens if the user is really trying to break the system? Does it break under those not everyday situations that you don't expect when you're writing the program, but is still a legal way that a possible way a user could interact with the system? Have you thought about what to do in that case? Again, document the tests that you write. That way you know what's been done. You should have some kind of document that doesn't require you to go through the actual testing files to know what tests you have written and what tests you have not. So documentation of testing can be as important as documentation for code. Automated testing, probably don't have to do too much validation of why this is useful. If you don't have to be involved in the actual test running, why should you be? The idea is that you will create a script. The script will run a bunch of tests and will output some log of what happened when that script was run. So this is why we use build tools, like for those of you working in Java, Maven and Gradle. If we want to be able to attach testing scripts to our build process, that's what allows us to do that. Be able to say, when you build, should we be able to run this code if some tests fail? Or should we know at the build step which of our tests failed? Maybe we make some changes to our code, it breaks something underneath the hood that we're not aware of, we want to be able to know that. That'll be inherent in the build structure if you've written some scripts that attach those tests to your code. This also allows you to run way more tests than you could run in person. You can attach thousands of user tests. Doesn't matter what they are. Throw everything at the computer as long as it takes a reasonable time and you're okay with the build taking that long. So there is trade-off there. If your tests take 10 minutes to run, it's going to add 10 minutes to the building process, which may not be advisable. General strategy for developing them, start with the unit tests. Of course, if you try to do a system test and there are 50 bugs in your program, then the system test is going to fail. Why is it going to fail? Now you suddenly need a recursive process that will eventually break it down to the units, to the modules anyway. So think about this more bottom up than top down. Start with each individual unit, write the unit test for that, fix the obvious issues with the units, with the modules, and then start building up for the system testing from there. So start with the unit tests, move on to the integration tests as you integrate together, build up to the system tests that require all of those pieces to already be in place and work together to the best of your ability from those integration tests. Then you write the system tests. And from there, once you have a system that's designed as bug-free as you can make it, then you get the acceptance testing from the end users. So that's the typical timeline on testing. Start in the small, move toward the large, then move toward more people in development. Questions on anything so far? We can think of these scripts that we use as called test suites. This is just a kind of program of a list of tests that need to run that are attached to some process. You'll want to separate these. You can even make suites of suites. So kind of break down your tests into the different components. Maybe you want to run some tests on an hourly basis, some tests on a daily basis, some tests on a monthly basis. If we want to have something that, for instance, maybe you need some maintenance time on a weekly basis for your application, this would be the time to run all of the tests, the expensive tests that make sure that everything is still working the way that you intend them to. And that way, on the hourly basis or the daily basis, it's not getting in the way of people utilizing your application, and you can run more of the faster, more critical tests. All right, I have a question for people. Let's say we've written a piece of code that has 3 if-else statements. And they're inside of each other. So we have kind of if, else, else. How many possible paths are there through this code? Different sequences of instructions run in different orders. Yeah,
I was thinking if we can test the inner F statement, then it means the other above them has to test. So if it made it to that point, means it passed the other steps.
It's conditional, and if it's a binary conditional, it means it has either true or false, that's two. So then with, if there's three nested inside of it. Let's see, you use that to the n power of them cases. So then, you have one with three inside of it, let's go then. Probably like 2 with 4 cases is what we have.
it's close. it is 2 to the third. So we want it kind of a, you can either be the if else, if else if else, else if, else if else if, and else.
Or switch statements.
Well, regardless, even if you use the switch, you still have those 8 cases. Because those are all going to be different sequences of instructions. So you really need 8 passes through this code in order to really fully test all of the ways that a user could interact with it in some capacity. That seems reasonable. What happens if there are 20 if statements?
Definitely 2 to the 20, because now we're.
There's a good approximation for 2 to the 20th. So 2 to the 10th is 1024, so it's pretty close to 1000. 1000 times 1000 is the equivalent of 2 to the 10th squared, or 2 to the 10th, 2 to the 20th.
Probably 100,000.
It's a million, 1,000 times 1,000 is a million. So you can see that the answer to the 2 to the 20th problem is pretty close to a million, 1,048,576. But if we're writing one test for each of these, 3 if else's is doable. 8 unit tests for one block, not the end of the world. 1,048,576 unit tests for one piece of code that has 20 branching points is now suddenly really scary to think about. So this means that we need to kind of group these cases together and think about, if I needed to write just 10 cases, 10 tests for these million cases, what 10 tests should I write such that if there's a failure somewhere in this, it is most likely that one of these 10 cases, these 10 tests that I write, will catch it. That's a much more difficult problem. It requires you to have a really good understanding of this code, how frequently users will go through different paths through this, how likely each of those paths are to be correct, to have a bug in it, what happens. You actually use critical thinking at that stage to figure out what to do, where to go from there. You can apply this kind of thinking to other kinds of structures, to recursive structures. This is why we talk about computational complexity. It doesn't just matter for runtime. It doesn't just matter for memory. It can actually matter for things like the number of tests that you need to write to verify that it works. So I'll stop there for the day, but we'll come back and talk about this a little bit more in detail, but it's all related. Judy.
So if we use all the time, the driving problem is
Right. The design you need to be everything to do to get all. It's gonna have it. You can all walk, right, there's a very end, and the scripts will come together. And you'll see all the other is explaining how to get that, you know,
You guys remember that? You guys read just time?
Also got to work.
3:15. Trying to, finalize stuff and all.